examples on how to solve sum of a GP or an exponential sequence, right? That was Mark 6. So this will be Mark 7. Perfect. So on Mark VII, we'll continue with some of the examples. Let's take this example. Find the sum of the first 13 terms of the GP. This is a GP. Leaving your answer in exponential form. In exponent form, sorry. So what's the formula for sum of a GP? It depends on the common difference, on a common ratio. So let's find the common ratio. R is equal to u of n plus 1 over u of n. That means that if we are using this sequence, we'll take, for instance, 1 over 4 divided by 1 over 2. And that is the same as 1 over 4 times 2 over 1. That is 1 over 2. So the common ratio is 1 over 2 half. That means that to find our sum of this GP, we're going to use this formula. And A from here is 1 over 2. And then N is 8. It's 13. We want the 13th element. Over 1 is half. That gives us half, right? Multiplying 1 minus half over 13 all over half. The answer in the end is 1 minus 1 over 2 exponent 13. So that is the perfect answer. That's the form they want us to leave it in. So if you don't understand this, just know that we use this formula, right, instead of this formula because n, which is, sorry, r is less than 1. When it's less than 1, we use this one. When r is less than 1. When r is greater than 1, we use this side. So that is it for this question. Let's try this question 2. Question 3. The third term of a GP is 10. So we have a GP, the third term is 10, and the sixth term is 80. Find the common ratio and the first term and the sum of the first 6 terms. Well, so we know the formula for a GP. So u of 3 should be given by AR exponent 2. We know u of 3 to be 10. We know A, we don't know A, and then we don't know R either. So we have this. This is equation 1. Let's just keep it. Let's try another one with u of 6. U of 6, the sixth term will be given by this right? Which is 80 is equal to AR exponent 5. This is equation 2. Now looking at these two equations, if we divide equation 2 by equation 1, let's see what will happen. 10, that will be 80 is equal to AR exponent 5, right? Divided by 10 is equal to AR exponent 2. What will happen here? 80 will be divided by 10, we get 8. A divides A, we get 1. And then R, when the R's divide, we get R exponent 5 minus 2. You know this. This is indices. So in the end, we get 8 is equal to R exponent 3. Now let's try and find R. How do we find R? Let's solve R here. You know, we can change 8 to 2 exponent 3. In R exponent 3. If this is the case, then R is equal to 2. So R is equal to 2. The common ratio is 2. What is the first term? If we want the first term, we can use equation 1 here and make A the subject. So let's make A the subject in equation 1. A is equal to 10 divided by R squared. 10 divided by, what's R? 2. 2 squared. That's 10 divided by 4, giving us 2.5. Perfect. So that's A. And then the first 6 terms, the sum of the first 6 terms. Sum of the first 6 terms will be given by, considering that R is 2, sum of the first 6 terms will be given by A into brackets R minus 1, Rn minus 1 all over R minus 1. So A is 2.5, R is 2, N is 6 minus 1, all divided by R 2 minus 1. That will be the denominator making 1. So we have 2.5 multiplied by 2, 6 minus 1. If you compute this with a calculator, you get 157.5. And that is your answer. Right. There are other examples here that have solutions and are very simple to solve. They are very, very simple to solve. Right. So let's move on to the next subtopic, which is the sum to infinity of a geometrical progression. So sometimes we have the sum to infinity, like sum to the very end of the sequence. So when the common ratio is less than 1, then we can find the sum to infinity, right? So sum n is equal to A exponent 1 minus Rn over 1 minus R. And when R is less than 1, right? And n is very big, it's infinity, right? N is infinity, and then R is less than 1. Then it means that when at these conditions, we will end up having a very small value, a very small value here, right? A very small value here, because a fraction raised to a very big exponent becomes almost 0, right? Becomes almost 0. So a n minus infinity becomes approximately equal to a, right? Because all this becomes 1. So it becomes equal to 1. It becomes approximately equal to 1. This infinity becomes approximately equal to 1, right? Because becomes approximately equal to A because all this approaches 1, right? So in the end, we get A over 1 minus R. So if you want the sum to infinity, which is only valid when these conditions are met, R should be less than 1 but greater than -1, then we'll use that formula. So let's see. Let's try this example. Find the sum to infinity of the following exponential sequence. We have 1, 4 over 5, 4 over 5, exponent 2, and then it goes on. Wait, is it 4 over 5 or 5 over 3? Whatever it is. So, looking at this, the common difference will be 4 over 5. Common ratio will be 4 over 5. Because we'll be running to end. The common ratio is 4 over 5, which is less than 1. So the sum to infinity is E 1 over 1 minus R. This is R 4 over 5, which becomes equals to 1 over 1 over 5, which is equal to 5. Right. You can do same here. First term, find the common ratio, and divide. It's very simple to find the sum to infinity. So right, that is it for series and sequence. If you all you have to know is one, you have to understand the concept. Once you understand the concept, you know your formulas. Right. So we have the formulas for the terms. We have formulas for the terms. For terms, we have AP, and then we have GP. And then you need a formula for the sum. That one. We also need an AP, and then we need a GP. And then we need formula for sum to infinity. And then you need to know how you change subject in equation, because you will definitely be finding different variables in your formula. And then so basically that's it. If you understand the concept, you memorize the formulas, then you know how to do change of subjects. You should be able to do every series and sequence question that you get. It's very simple. Or the examples here are so simple. You will get them. And some examples feature string and series and solving simultaneous equations. Yes. Some examples feature simultaneous equations, so you need to know them too. Perfect. I think we are good to go now.